Okay, this is the section 2, chapter 5 again. In this video, we are just going to explain the having magnetic field in the solenoid, which is similar to the coil, you know that. But we're going to change little things. Actually, two things will change in the formula, one of them, and in the direction, indicating direction, we're going to have something else. First of all, we know that when the current goes around, it goes through the wire. In that case, the magnetic field will be concentrated around the wire. And later on, we bend this wire into the coil, and then we change it to the solenoid. Now, for the solenoid, first of all, we have to know about the solenoid. Solenoid is the shape of it is kind of like this one somehow, and then is a long straight wire is bent into a coil of several closely spaced loops. The resulting device is called solenoid. So in another word, we can say solenoid, a long helically wound coil of insulated wire. The magnetic field is going to be produced around that solenoid if the current goes through the solenoid. And you have to know that inside the solenoid, we will have stronger and higher magnetic field. And the formula, it's near to the coil, mu naught Ni, again, instead of saying 2R or 2 pi D, we're just going to say L, which is L stands for the length of the solenoid, as you see, length of the solenoid. In the meter, of course. This is the little change that we had in the formula. The second change that we will have is the indicating direction. Till now, we just said the thumb is going to show us the direction of the current. And this forefinger is going to show us the direction of the magnetic field, B. Now we're just going to switch the places and then we can indicate the direction. For example, we will say the thumb is going to be the north pole of the magnet, which is we can say that's the direction of the magnetic field. And this forefinger, it's going to tell us the direction of the current. As you see, the current is going up inside the solenoid, over the solenoid, let's say. So we're going to align our fingers according to that arrows, okay? So do not forget that we just switch the place of the magnetic field and the current. Before we were saying current is the thumb and forefinger is the magnetic field. Now we're just going to say that magnetic field is going to be the thumb, or this thumb points the north pole and this forefinger shows us the direction of the current. Let's have an example how to indicate the direction of the current. Imagine if we have a coil, which is the coil, the solenoid. It's like this. Like this one. As you see, the wire is going from the behind of the solenoid and front also. That's going to be the left and that's going to be the right side. Now, if I show you the direction of the current, and the question actually is going to be in this way. That's the direction of the current. The current is going through that wire from the right to the left. We're going to follow the path. That's the direction of the current. Now, for answering that question, how you can say the magnetic field is into that direction, or which side of that solenoid it's going to be the N side, which side is going to be the S side, like this figure that we have. Okay, so let's follow the direction of the current. When we follow the direction of the current is going to go behind of the solenoid and comes back over there. Again, as you see, it's coming down and then goes the backside and then comes down. So in all of them, it's just going to be the same way, which is coming down, and then that's going to be the true path of the current. So now the red one is the current. If I want to find the direction of the magnetic field, so I have to align my four fingers from the right hand rule according to that arrows. So those four arrows shows as the forward one, to downward direction. So I will align my right hand rule somehow in this way. That's going to be my thumb. and that's going to be my 4 fingers. I'm not good at drawing, but I'll try my best. Okay, and then, you know, that's going to be the fingers, and then, okay. So as you see, this is going to be the thumb, and which is showing us the direction of the North Pole or direction of the magnetic field. And this is going to be the direction of the current, which is this 4 finger is showing me. This 4 fingers is showing me. So now this part is going to be the North Pole, this part is going to be the South Pole. Okay, let's have another example in opposite way. I will not give you the direction of the current, I will give you the direction of the magnetic fields. So let's have another coil or solenoid, sorry. So the wire is going and it's coming down like this, as you see. Now, if I say this is the North Pole of the magnet, that's the South Pole of the magnet, how can you indicate the direction of the current? Okay, how could you indicate the direction of the current? First of all, I have to direct my thumb according to the North Pole. This is going to be my thumb, right? I said I'm not good at drawing, but I'll try my best. That's going to be the direction of the thumb. So this is going to be my hand. And then the 4 fingers, it's going to be just somehow like this one. Oops. Okay, this is going to be the 4 fingers, which is showing me the direction of the current inside this wire. As you see, for my 4 fingers shows the up, so the current should be going to the up. So if I follow this one, look, it is showing me the up. So it comes from that direction to that one direction, and then, yeah, up, and then goes down, and then comes from the behind, from the left to the right. Direction of the current is from the left to the right. Sorry for the drawing, I don't know that much, but the drawing, that's why. Okay, so I hope you understand from that 2 examples. Okay, we have this question. How can you increase the strength of the magnetic field inside the solenoid? How I can increase the magnetic field? If I increase the number of the solenoids per unit length, it means if I increase more, if I have more turns in a less current, less length, less distance, I will have more magnetic field. That's correct. Increase the current, that's also correct. Place an iron rod inside the solenoid. It means you increase the magnetic permeability, mu naught. If you change that constant, it's 4 pi times 10 to the power -7, right? So if you change it to another number, like 4 times 10 to the power -2, in that case, you increase that number, and then you increase the magnetic field. So that's why the answer is going to be all of the above. Okay, let's go for some questions about that. Problems that formula that we study now. In this question, sample problem, the question is telling me it is the solenoid. It is not a straight wire. It is not the coil. It's solenoid. So look at the number of the turns is a lot. That's n. Of the length 70 centimeters. So it means 0.7 meters. That's going to be what? Length, of course. It should be small length. Calculate the magnitude of the magnetic field in the middle of the solenoid, and the way from it, it is ends when the current of 4.7 passes through. 4.7, it means that's the I, which I wrote them all over there. Now easily we will plug in the formula. Mu naught Ni over L. So B is equal to, mu naught is 4 pi times 10 to the power -7, constant, times N is 1,400, times 4.7 over 0.7 meter. So when you calculate this one by the calculator, you're going to get 1.2 times 10 to the power negative 2 Tesla. Okay, this is going to be the answer of that question. We have another question, by the way. The second two parts question. The second part is quite easy, but the first part, there's a little note we have to know that, and it's auxiliary questions. A solenoid of a length 50 centimeters. So it means L is given, L is equal to 0.5 meter. And the N is equal to 2,000 turns. Okay, turns. Now the question is telling you, question A, calculate the number of turns per unit length. It means divide N over L, how much you're gonna get? Tell me. N divided by L, which is equal to 2,000 divided by 0.5, which is going to be equal to 4,000 turns per meter. That's going to be the number of the turns per unit length. And the second part, you already know that B is equal to the mu naught and I. Mu naught you know, and the number of turns 2,000, and the current is 10 ampere. It's given and divided by 0.5, which is the length. You're going to get 0.05 Tesla. Quite easy, right? Okay. What is the intensity of the current? In that example, current is not given. We're going to write down the formula, mu naught N I over L. So what is the B? As you see, it's 60 pi times 10 to the power negative 3. So 60 pi, times 10 to the power negative 3 equal to mu naught 4 pi times 10 to the power negative 7. And then N, it's given already 1,500. Time is the current, which is a noun. Over the L, which is 100 centimeter equal to 1 meter. So now I can cancel pi with the pi. And I can cancel 7 with the 3. Negative 4 remain. And this negative 4 will be cancelled by this 2. It will remain negative 2. And then you can just multiply 4 by 15, which is equal to 60. 60 divided by 60, it is going to be equal to 60 divided by 60 is equal to 1. And then we're going to find I, it's equal to 10 amperes. Okay. This is how you're going to find the current. Next question we have, it's a auxiliary question, by the way. A solenoid with the 1,000 turns, you have 1,000 turns. What is the length? L is a noun in that question. And the solenoid, if the number of the turns per unit length is equal to 2,000 turns. Guys, we can solve this question in two ways. First way and the second way. The first way, I have N over L. I have N over L, which is equal to 2,000. And I have already have N, which is equal to 1,000. So now, if I just want to find L, you know that, what should we do? We just simply goes to that formula. N over L is equal to 2,000. You already know that in this one. And instead of N, we're going to write 1,000 L equal to 2,000 L. So you know that if you have to find L, you have to say 1,000 divided by 2,000. You're going to get like 0.5 meter. This is one of the answers. And the other one is just going to, you just need to divide 1,000 by any of those numbers. You must get 2,000. 2,000. So if I divide by 30, cannot be, 40 cannot be, and 5 meters cannot be. If I divide it by 0.5 meter, in that case, I will get 2,000. I will get 2,000 in this case. Okay. So the choice C, it's going to be the correct answer. As you see, we get 0.5, which is equal to 50 centimeter. Okay, I hope you get it, that question. And we have another question from the chapter review, which is going to say, what factors does the strength of the magnetic field of the solenoid is depend on? Number of the coils per unit length or amount of the current. And you know this constant, that's why we are not going to talk about the mu naught. I hope you understand the video, and we're gonna keep going with the next questions.